So, hello my dear, I welcome you all in this series of one-to-one session. In this series, we will discuss concept plus practice. The subject is fluid mechanics and the topic is flow over the external surface part 5. Already we completed part 1, part 2, part 3 and part 4 of the viscous flow over the external surface, that is the boundary layer over the flat surface. So, just we look at this one. My dear, before I start this lecture, I will give you some information about the IMS features. What is that? If you are joined the live online program for the 25-26 of the GATE, what you have to get? You get 800 plus hour of live classes with live interaction, theory book and also exercise book. In this exercise book, 4,000 plus question is there and all the questions are bifurcated by level, level 1, level 2 and level 3. And also you have to get 34 plus year of GATE question bank with a video solution, okay? And also 12 personalized one-to-one mentorship program also there, and also 130 plus online test series is there with a video solution of a mock test and many more. So, book for a free counseling session, click on this given description below and also call on this number if you want to any clarification of any your question, okay. Now also there is a IMS Telegram group. If you join that, what you have to get? You get a schedule for free YouTube lecture like that. Lecture PDF, after finishing all the classes, we upload the PDF on the Telegram group. Important updates related to the seminar and webinar. The information about the government job like PSUs, okay. Expert session of the important topic of any topic of the expert sessions and daily quiz and many more. So if you want to join this Telegram group, that is a free cost. Okay, now my dear, so we start this. Already we finished this Navier-Stokes equation and what is the importance of this equation, and also we have to develop the concept of a boundary layer, how this boundary layer form, what is the equation of a boundary layer, and also we have to discuss with the order of magnitude method how the shear stress, how the displacement thickness, how the boundary layer thickness, how the skin friction coefficient, drag coefficient, all this property parameter will vary. And also we have seen this, if the fluid is moving fast, what is the boundary layer, and if the fluid is moving slow, what is the boundary layer. All we are seen in the previous lecture. That means what is the conclusion of the previous lecture, previous 4 lecture, what is the conclusion? Conclusion is that we are able to understand what is the boundary layer theory. That means we already discussed with what is the boundary. Someone asks you this question. This is very important question. Always keep in mind, and accordingly you have to revise this lecture. What is the boundary layer theory? Okay, what are the boundary layer equation? What is the different type of a boundary layer equation? Why it is important? That means why we study the boundary layer, and what are the assumptions of a boundary layer theory under which this theory will valid. These all questions we have to complete it during the 4 lecture. 1 lecture, 2nd lecture, 3rd lecture and 4th lecture. These all the question all the answers we already discussed up to the lecture 4. Now what is the motive of today's lecture? The motive of today's lecture, we are concerning with the another approach of a boundary layer, and we'll also derive the equation and for the skin friction coefficient, drag coefficient, shear stress, boundary layer thickness, all this, but the method number 2nd. Previously method is the very simple method, that is the order of magnitude. Now we will discuss the 2nd method, that is the moment integral equation. You know this thing, the moment integral equation. That means someone asks you the Karman moment von Karman integral equation. That means we find all the parameter related to the boundary layer according to the momentum integral, von Karman integral equation. Von Karman integral equation. So beta, what is the von Karman? What is the of what equation you have to integrate? The integration of the equation of the momentum equation. That means this is the momentum integral equation. That means you have to integrate of the momentum equation. okay, for the equation. So boundary layer have the equation all will exist in x direction equation, and y direction equation is 0. That means dp over dy is equal to 0. So we are not bothering about the moment integral method, moment integration of the moment of a y momentum equation. We have to bother about the integration of the x moment. So von Karman moment integration, what is the net result of the equation? That equation is valid. This is very important for the turbulent as well as laminar flow. That means that equation, after the integration of that momentum equation, x direction momentum equation, what you have to get, that is that equation you apply frequently for the both laminar as well as turbulent boundary layer. That is good. Okay. So we take the example flow over flat plate. That means we have to derive the equation of the momentum integral equation for the flow over the flat plate. Okay. So we know that what is the momentum equation of the flow over flat plate? U dou u by dou x plus v dou u by dou y plus this is your transverse diffusion. That means the momentum diffusion of a momentum disturbance in a transverse direction, mu du square by dy square. Now we integrate. Why? Because the name itself suggests that the integral, that is your integral. That means you can integrate this equation. So integration, the limit is 0 to y. Y is what? Y is the boundary layer thickness, up to which the velocity is approximately the free stream velocity. So you have to integrate 0 to del u dou u by dou x, and integration with respect to y, 0 to del v dou u by dou y integration of dy, plus is equal to 0 to del kinematic viscosity dou square u by dou square into dy. Once you have to integrate, why? Because in between there is a lots of mathematics. We are not bothering about the mathematics for the GATE syllabus. Only we have to discuss with the what is the physical meaning of this equation and what is the implication. What is the implication of this equation? So finally, if you derived it with the integration, putting all this value, so you have to get this equation. That is the equation is the von Karman integration equation. That means momentum integral equation. If you integrate the boundary layer momentum equation, that equation will derived finally wall shear stress divided by rho u infinite u free stream velocity k square is equal to d by dx integration 0 to del u by u infinite into 1 minus u by u infinite dy. Always remember this equation. What is the von Karman integration equation? The von Karman integration equation is shear stress, that is your wall shear stress divided by the rho free stream velocity is equal to in d by dx integration 0 to delta u by free stream velocity into 1 minus u is the local velocity, is any point within the boundary layer, divided by u infinite into dy. Now, so how we apply this equation, that is a very important. That is the very important. So to solve this equation beta, to solve this equation, we must have to knowledge about the velocity profile. That means we have to know about the u by u infinite. So in the question always given u by u infinite in the function of y by delta. Y by delta. So we write some step by step and then we will discuss. Okay. What is the first? What is the step? See, this is the step. That means in the question u by delta, u by u infinite, that means u is the velocity within the boundary layer and u infinite the velocity above the boundary layer is a function of y by delta. It is given in the question. Don't bother about that, sir, where it is given or not. No, it is always given in the question. Now, we know that this is a momentum integral equation. Tau wall by rho u infinite square is equal to d by dx 0 to delta u by u infinite 1 minus u by u infinite into dy. You know this thing. Now, from here, if you put this function u by u infinite and integrate it, so once you have to integrate, the relation comes out to be this equation. That means this is the equation number first. After you putting this value y by u infinite in the form of y by delta, putting this value, solve it. After the solving, you get this nature of this equation. That means there is a some numerical value, there is a some constant into d delta by dx. That is the equation number first. So from here, this first equation you can find wall shear stress with the help of momentum integral equation. Now, the second equation, we know that for the Newton's law of viscosity, for the laminar boundary layer, for the Newton's law of viscosity, tau is equal to mu du over dy at a wall y is equal to 0. That means if this is your plate, this is your y direction. So at y is equal to 0, tau is equal to tau wall. So you have this du over dy, that means this you have u is equal to u infinite, a function of y by delta. You just integrate it, du over dy, put y is equal to 0, find it, multiply with the dynamic viscosity. So you have to get this wall shear stress in the form of boundary layer thickness. So this is the second equation of wall shear stress. Now this is the first equation of the wall shear stress is due to the momentum integral equation, and this is the second equation is due to the wall shear stress of Newton's law of viscosity. So first we have to apply the momentum integral equation to find the wall shear stress, then you apply the Newton's law of viscosity, find the wall shear stress. So two wall shear stress is there. Now you equate it. That means this wall shear equate it. After the equating, you get the equation in the form of delta and x. You have a equation in the form of quadratic equation or any type of nature, sinusoidal or any type. Display boundary layer thickness and the x is the linear distance of the plate. So x and delta and x, you have a relation in the form of equation. Now, in the form of equation, there is a one constant term. So, how to find this constant term? Apply the boundary condition. What is this is the very basic boundary condition. What is that? At x is equal to 0, that means at a leading edge. At a leading edge, there is a, that means this is your, if this is your plate, so at this is your delta, so at x is equal to 0, delta is 0. There is no any boundary layer thickness. So delta is 0. So at x is equal to 0, delta is equal to, put this value, find the value of c, then you have an equation in between x and delta. Now once you have to x and delta, you have to find the delta at any local x. So once you have to find the delta, boundary layer thickness at any cross section x, then from the second equation, this is the second equation, put this delta value. What you have to get this delta in the form of Reynolds number, very important. You have always, all the parameter you have to derive it in the form of Reynolds number. So once you have to get this delta, boundary layer thickness, in the form of Reynolds number, put this boundary layer thickness into the equation number second, which is in the form of delta. Put this delta in back, find the wall shear stress. Once you have to find the boundary layer thickness and wall shear stress, you can easily find the local skin friction coefficient. What is that? Wall shear stress, just now we have to find it, divided by dynamic pressure, half rho u infinite, u free stream velocity ka square. Just now we have to find it in the form of Reynolds number. Okay, no problem. Now, how to find the drag coefficient? Drag coefficient is drag force divided by the area of dynamic force. Half rho u, this is the pressure, into b is what? Width of the plate. L is the length of the plate. So you have the area of this one. So once you have to find it, how to find the drag force? You just to take a elemental part of the plate, dx, and then you have to derive it 0 to L, integrate 0 to delta, find the drag force, put this value drag force here and find the drag coefficient. These are the method of how to proceed with the von Karman integration equation. Once you have to understand this step, we'll go to the one example. What is that? See this example. This is the example. What is that? See this example, my dear. I will read this example first. What is that? The velocity profile for the laminar boundary layer developed over the plate of width B. Plate width B it is given, and the length of the plate L it is given, approximated by the parabola. This is the parabola, that means u by u infinite, this is a free stream velocity, is given. See, this is your u by u infinite. U by u infinite is the function of y by delta. It is given. First step it is given. What is that? Minus y by delta whole square plus 2y by delta. It is given in the question. Already we'll see. Already I told you this, it is given in the question. So this is given in the question. Now, and this you know this thing, the flow over flat plate, well, this is a free stream velocity u infinite, free stream velocity, and there is any velocity. So ratio of this velocity within the boundary layer and above the boundary layer, the velocity relation it is given. Okay, now we have to find it, determine as a function of x the thickness, boundary layer thickness, skin friction coefficient CF, and drag coefficient CD. These are the very basic parameter you have to find when you have studied the flow over flat plate. What do you have to find? Boundary layer thickness at any x, skin friction coefficient x, and the drag force over the entire plate. These three parameter always find. Someone asks you, what is the importance of the boundary layer? Sir, we have from the boundary layer you can find the skin friction coefficient, drag coefficient, boundary layer thickness, wall shear, all the things. Now, start with that. What is this? This velocity profile it is given. Now, from this velocity profile, with this velocity profile, we will be put in the von Karman integral equation. So, we have to put this velocity profile, it is given in the question. It is given in the question. Now, we know this thing, this is according to, we know this thing, this is our momentum integral equation, MIE. Now, this momentum integral equation, we put u by u infinite here. So, u by u infinite is equal to minus y by delta whole square plus 2y by delta, minus y by delta whole square plus 2y by delta. This is your this term. Now, 1 there is a minus, so minus this minus plus minus of this minus, so minus 2y by delta dy. Now, there is a mathematics. If you are strong in mathematics, then you have to able to solve this equation. Now, after solving this equation, after integrating of this equation, it's your homework, just your practice. If you integrate this equation, we already told that there is a relation between the wall shear stress and d delta by dx, and there is some constant. So, this is constant is k. See, match this line. So, this constant k you have. So, according to this velocity profile, what is the constant? 2 by 15. 2 by 15. So, tau wall. So, what is that? Tau wall by rho u infinite square is equal to 2 by 15 d delta by dx. So, first equation, that means first equation, that means in the form of wall shear stress you got it. So, this is the first equation. Now, we equate this wall shear stress. So, we find the second wall shear stress from the Newton's law of viscosity. So, if you apply the Newton's law of viscosity, you have a velocity profile. So, you have this velocity profile already given. You just integrate with respect to y. If you integrate with respect to y, put y is equal to delta. So, you have du over dy at y is equal to 0, this one. Yes or not? Du over dy at y is equal to 0 is equal to 2 free stream velocity divided by delta. Put this value du over dy at y is equal to 0, this value. So, this is the second equation. Now, the first equation of the wall shear stress also this equation we derived it from the von Karman integration equation, and this wall shear stress will derived it according to the Newton's law of viscosity. This is also wall shear stress, this is also wall shear stress. We equate these two equations. So, we equate these two equations. Now, equating first and second, this is equation number second. Equating first and second. So, we are removing this wall shear stress, this wall shear stress equate. Now, after equating, we have this relation del d delta d is equal to 15 mu rho u infinite dx. Okay, now we have to integrate this equation. After integration, there is some constant value c. If you integrate it, del square by 2, 15 mu divided by rho u infinite x plus c. Now, how to find this c? Apply the boundary condition. What is the boundary condition? At x is equal to 0, delta is equal to 0. So, put x is equal to 0, delta is equal to 0, so c value is 0. Finish. So, what is the final equation then? This is the final equation, delta square by 2 plus 15 mu x rho by u infinite. So, up to this step it is finished. That means apply boundary condition at x equal to 0, delta is equal to 0. You have to find the relation between x, delta and x. Once you have to find the relation between delta and x, just you have to find that boundary layer thickness. So, once you have to find the delta and x relation, find the boundary layer thickness. So, just equate it, we have to multiply intuitively x by x. Why? Because we have to convert this equation into the form of Reynolds number, local Reynolds number. Okay. So, just you have to arrange it. After arranging, this is your boundary layer thickness. This boundary layer thickness is the function of local Reynolds number. Okay. Okay. So you have this boundary layer thickness. So first answer is got it. What is the first answer? You have to find the boundary layer thickness at x. So what is the boundary layer thickness according to this profile? According to this profile, this is your boundary layer thickness. Now, if you find this boundary layer thickness, we already told you, if you find this boundary layer thickness, put this boundary layer thickness in the equation number second. What is the equation number second? This is your equation number second. This is your equation number second. So in this equation, put this value of delta. Find wall shear stress. So in this equation, see, delta. Put this delta in the wall shear stress. What is that? See, this is a wall shear stress. Put the value of delta from the equation number second. From the equation number second, this is your tau wall is equal to 2 mu u infinite by delta. This is you have a delta in the form of Reynolds number. Put this value back here. So if you put this value back here, delta, so this is your delta. So put this delta here back, rearrange it. So this is your wall shear stress. This is your wall shear stress. After rearranging, this is your wall shear stress. Once you have the wall shear stress, you can easily calculate the local skin friction coefficient. Local skin, why? Because this is a local Reynolds number, REX. It is not REL. This is your REX. That means the Reynolds number at any location of the plate, X location. So this is your local skin friction coefficient, wall shear stress divided by dynamic pressure. You have already wall shear stress, put this value of wall shear stress and then divide it half rho u infinite square. Now you have to rearrange it. So 2 above, this is your 0.732 REX rho u infinite, this will take downside, then this is your nature. So what is the local skin friction coefficient? 0.735 root under REX. So this is your second. So this is your first answer. This is your second action, skin friction coefficient. If you find the average, so this is your local. If you find the average skin friction coefficient CF, already we'll tell that in previous lecture, 0 to L CFX dx. Put this value of CFX here, integrate it, find the, this is your average skin friction coefficient, this is your local skin friction coefficient. Now we have to find the drag coefficient. So drag coefficient, if you find the drag force divided by the dynamic force. What is the dynamic force? Dynamic pressure into the area. What is the area? B is the width of the plate, L is the length of the plate. So total area is B into L. Now the question is how to find drag force. Already we'll discuss in the previous lecture. So how to find the drag force? To find the drag force, this is our plate. We select the elemental of the plate. So on that element there is a wall shear stress. Why? Because wall shear stress is continuously vary. So we have to take the elemental part of the length dx and the width is b. So if find the drag force, you just multiply. What is the force? Stress into area. So the wall shear stress, and what is the area on which it is acting? This area dA. What is this area dA? This is your b into dx. Okay, so from here we integrate 0 to L, put the value of wall shear stress, which already got it, wall shear stress from here. This is your wall shear stress, already we have got it, na? Wall shear stress from here, we got it, the wall shear stress, this wall shear stress, this is wall shear stress, this wall shear stress, put this value of wall shear stress back into the drag force equation, put this value. And then we have to solve this equation, 0 to L b into dx. We will take 0.356 outside, dynamic viscosity outside, u infinite outside, b is the width of the plate outside, rho mu infinite, mu free stream velocity by mu outside, integrate 0 to L, left it is your square root, this x, that means square root of x and this x is equal to minus of 1 by 2. So integrate it. If you integrate 0 to L, this is 2 root L. Multiply it, 0.365 is equal to, multiply with the 2, 0.732. Mu u infinite into b root under rho u infinite. This L is inside the square root into mu. So this is your drag force. So once you have to find the drag force, put this value. Why? Because CD is equal to what? Drag force divided by this one. So once you have to find the drag force, put this drag force back, divide it, rearrange. Again you have to rearranging. After rearranging, the drag force is approximately 1.5 of the square root of average Reynolds number, yeah, total Reynolds number. So from this one you can get the drag force. So these are the implication, these all are the implication of the what beta? These all are the implication of the von Karman integral equation. Now once you have to got it, this von Karman integration equation, we have to solve another problem which is like that. What is that beta? See. This is your question. Flow over a flat plate of a velocity v. Flow over a flat plate of a velocity. This all velocity profile it is given. Yes or not? This velocity profile it is given. We'll solve this question first. We'll solve this question first, beta. Read this question. A flow over a flat plate. Please read this question carefully. Please read this one, beta. I request you, please read this question. This is given, velocity profile given, boundary layer thickness is also given. Please read this question. Please read this. Okay, so we got it, this wall shear stress, all the things we have to got it. Now, okay, 2 by delta, okay, clear. Flow over flat plate, this is also clear. Velocity 2 meter per second, okay, no problem, we'll got. So, what is that? A flow over a flat plate. So this is your flat plate, beta. This is your flat plate, and flowing it is there with plate with the velocity u, capital U. There is a development of a boundary layer, and this is your boundary layer thickness delta. Can be expressed as this is the velocity profile u by u infinite, and this is your boundary layer thickness. It is given. Don't remember. If the free stream velocity, that means this velocity, it is given 2 meter per second, and air has a kinematic viscosity is given, and the density it is given, rho it is given, the wall shear stress, very important, at what distance? X is equal to 1 meter. Simple. That means this is let's suppose this is your length L. We have to find at X is equal to 1 meter, what is the wall shear stress? What is the wall shear stress? So what is the given? We will first write the given. Free stream velocity is equal to 2 meter per second. Kinematic viscosity is equal to 1.5 cross 10 to the power minus 5 meter square per second. Density of the air, it is given 1.23 kg per meter cube. Okay, this is your plate. This is your plate, boundary layer. X is equal to 0, this is X is equal to L. Here there is X at any X is equal to 1 meter. We have to find the wall shear stress. At X is equal to 1 meter, we have to find the wall shear stress. Now, how to find the wall shear stress, my dear? We know that from the Newton's law of viscosity, wall shear stress is equal to mu du over dy at y is equal to 0. Now, the velocity profile it is given. U by u infinite 3y by 2 delta minus 1 by 2 delta by q. So you have to differentiate this equation. You have to differentiate. Once you have to differentiate, the value it is your 3 by 2 delta into u infinite. This is your wall shear stress. Just you have to differentiate. What is the u value? U is equal to u infinite. What is given, beta? U infinite 3y by 2 delta, 3y by 2 delta minus 1 by 2 delta y by delta q, 1 by 2 y by delta q. This velocity profile given, just you differentiate du over dy and put y is equal to 0. This is your value. What is this value? This is your value. That means u infinite 3 by 2 delta. Put this value back. So this is your wall shear stress. Now, what is the value of delta it is given? It is given 4.46 x divided by Rex, it is given. Okay, so if you find the delta, why? Because from here you have to find the delta value. So delta relation you have to find from the given relation. Why? Because the given relation delta it is given. The given relation delta, it is given. So for to finding the delta, boundary layer thickness, just you have to find the Reynolds number first. So this is your local Reynolds number. So Rex you have to find it. Rex is equal to what beta? Rho. Rex is equal to what? U infinite x divided by nu. Yes or not? Local Reynolds number. So you have U infinite 2 into x. At what distance you have to find? 1. And kinematic viscosity it is given 1.5 cos 10 to the power minus 5. So from here you find the Reynolds number 1.333 cos 10 to the power 5. So this is your less than 10 or 5 cos 10 to the power 5. That means this is approximately laminar. So this is your laminar. So put this value here back. So delta is equal to 4.46 into x ka value 1 meter. You have to find it. Reynolds number square root. This is your square root. So a square root of 1.333 into 10 to the power 5. If you find it, this displacement thickness is boundary layer thickness is 0.0127 meter. Once you have to find it, put this value back here. That means mu 3 by 2 delta you have. What is the delta? 0.0127. 1 second. 0.0127 you have, and U infinite you have. So this value you have, this mu you have. So from here you can easily find 4.36 cross 10 to the power minus 3 Newton per meter square. Clear? Clear? This is a very simple thing, very simple thing. This type of question, or this is the very basic question of the boundary layer. Okay, na? This is the very, very basic question. Don't ignore. Mechanical peoples must be, this is must be. Why? Because such type of problem will encounter with the chapter in the convection. And for the civil, this is the hot cake question. Why? Because each and every year this type of question will be appear in the GATE examination. So this type question, this is a very basic question. So what we have to learn today? We have to learn today what is the importance of the von-Karman integral equation, and how to find the von-Karman integral equation, how to apply the von-Karman integration, and what we have to find the final outcome of the von-Karman integral equation. And we will solve the one fundamental problem. So my dear, if you really want to like this video, please I request you beta, like, share and subscribe the IMS channel, so that you have to get a very good content, free content in the YouTube lecture. Okay. So I hope you like this video. Just for the next lecture, we will discuss the displacement and boundary layer, displacement thickness, momentum thickness on all the relation, and that is very good problem also. So please wait that lecture. Up to that, thank you. Bye-bye.